Hello guys, welcome back to my channel. My name is Gede Pasek Arya Sunanjaya. My student identification number is 23055-31072, and then my lecturer is Professor Dr. Tjokorda Gde Tirta Nindhia, MT M Eng from subject Metallurgy TM 2301. And today I want to show you my presentation about mechanical properties and strengthening mechanism. So guys, this is my profile for my presentation. So for my base reference book is Metallurgy for Non-Metallurgists, edited by author Reardon. 3.1 Mechanical properties. Definition: when a force or a combination of force are applied to a material, the material responds by deforming or straining, often in a complex manner. For example, when bungee jumper hops off of a platform, the bungee cord stretch dramatically, and at the same time its cross-sectional area decreases. Under normal circumstances, the bungee cord safely prevents the jumper from hitting the ground below. While this example describes a type of a deformation that is readily visible, often deformation of this type cannot be observed this easily. Important types of mechanical properties. Different types of tests which use an applied force can be employed to measure other mechanical properties as well. Additional examples of such properties include the elastic modulus, hardness, fatigue, resistance, and fracture toughness. These are described subsequently in more detail. A short list of the important types of mechanical properties includes hardness, as a measure of resistance to indentation. Linear, elastic, constant that relate to strain under tensile, compressive, and shear loads. Yield strength, under tensile, compressive, and shear loads, indicating the stress level required for the onset of permanent or plastic deformation. Ultimate strength, under tensile, compressive, and shear loads, indicating the maximum engineered stress that the material can withstand without fracture. Ultimate tensile strength, or UTS, typically is associated with the onset of necking of tension the specimens. Fatigue strength, indicating the level of cyclic stress that cause fracture due to metal fatigue over time. Impact toughness, indicating energy absorption from loads that cause very high strain rates. Fracture toughness, indicating resistance to fracture with pre-existing flaws or stress racers in the geometry of a part. High temperature creep deformation and stress rupture, where high temperature cause metal to permanently deform as a function time. Damping properties and wear resistant properties, due to wear mechanisms such as galling, abrasion, and erosions. 3.2 Strengthening mechanism. The underlying structure of metals and alloy, be it macrostructure or microstructure, microstructure, have an important bearing on their strength, ductility. The toughness, strength of material can be improved in various ways, as described in the following section. For example, a microstructure with finer grains typically result in both higher strength and superior toughness compared to the same alloy with physically larger grains. Other strengthening mechanisms are achieved at the expense of lower ductility and toughness. Thus, there may also be trade-off between strength and ductility depending on the material, the application, and the microstructural mechanism of strengthening. Solid solution strengthening. Solid solution strengthening is a mechanism that increases the strength of a metal through the careful addition of specific alloying elements, the insertion of substitutional and or interstitial alloying elements produce a strain in the crystalline lattice of the host. Solvent structure because the solute atoms typically have a different size than the host atoms. Effect of grain size. Grain boundaries are effective obstacles to slip because the slip of discolation or in the lattice of individual grains cannot easily cross the high energy barrier of grains boundaries. Instead, discolation are blocked and pile up at the grain's boundaries. Thus, grain's boundaries provide a source by strengthening by pinning the movement of discolation from one grain to another. Smaller grains in a crystalline material also mean that a greater percentage of the material consists of grain boundaries of strengthening. Cold working. If a metal is deformed at room temperature or up to approximately 0. Tm, where Tm is the melting point of or Tm or temperature, where temperature is the melting point, the absolute temperature scale, the microstructure becomes deformed due to cold working, also known as work hardening or strain hardening. During cold working, most of the energy dissipated in the workpiece as heat. However, as much as 10% of the energy is retained as stored energy within the metal in the form of vacancies, discolation, and stalking faults. The amount of stored energy increases with the greater amounts of deformation and lower working temperature. Cold working greatly increased the number of discolation, discolation and normal discolation. Densities on the order of 10 power 6 to 10 power 7 centimeter are increased to 10 power 8 to 10 power 11 10 power 11 centimeter cubic during cold working. Three distinct processes can occur during annealing. Annealing is often employed as an intermediate step in the cold working process to reduce the internal stresses in the material and increase its ductility so that it can undergo further cold working without introducing microscopic defects such as cracks during annealing. Three distinct processes can occur. 1. Recovery, which relieves some of the stored internal strain energy by rearrangement of discolation into lower energy configuration without any change in the shape of orientation of grains. Recrystallization, which is the replacement of the badly deformed cold work grains by new strain-free grains. And last, grain growth, which occur when some of the recrystallized grains grow at the expense of the recrystallized grains. Back to Dr. Wilm's mystery. The good doctor discovered a process now known as solution heat treating and natural aging. He also designed an alloy or duralumin suitable for strengthening by this process in what is now known as precipitation hardening. Three zone of hardness. The basic stage of precipitation hardening is illustrated by the fig and with hardened polyethylene against the time. The increase in hardness with time is known as precipitation hardening or edge hardening. In zone 1, submicroscopic precipitate particles are being formed as the alloy attempts to reach equilibrium. Solute atoms diffuse through the solvent lattice and segregate to form a few very small particles, a stage in which solute atoms are grouped or rearranged so they can begin to form a precipitate. This result is a slight increase in hardness. In zone 2, maximum hardness is reached. The solute atoms move about and form small particles, attempt to form the precipitate phase. The precipitate remains coherent with the aluminum lattice. Strength increased significantly. In zone 3, the precipitates grows in size with continued aging and tend to become non-coherent. The loss of coherency, reduced lattice stresses result in decreased hardness. Other important strengthening mechanism. Definition: dispersion strengthening is an active mechanism in alloy intended for use at intermediate and elevated temperature. Is in many ways very similar to edge hardening. The difference lies to the precipitates themselves. The particles are chosen because of their thermal stability, that is, their resistance to particles coarsening or growth at high temperatures. In contrast, the edge hardening or heat treatable aluminum alloy consists of precipitates second phase depressions that are not particularly thermal stable. Dispersion strengthened alloy are usually those that contain a dispersion of particles with extremely low solubilities and diffusion rates in metals. An example of a dispersion strengthening phase for high temperature application are the rare earth oxides used in producing oxide dispersion strengthening or ODS alloy. In this ODS alloy, the solubilities of both the rare earth and oxygen tend to be very low, typical matrix or nickel and aluminum. Sorry, and the diffusivities of the rare earth elements are also low. So guys, that's all of my presentation. Thank you for watching. Sorry for my misunderstanding words and see you on the next video. Bye bye.